Hello and welcome to the 5th Porous Media Tea Time Talks. The goal of these seminars is to give junior researchers working on porous media the chance to present their work. Of course, this is meant to be complementary to the geoscience and geoenergy webinars, which you can find in our featured channels. My name is Tom Bultrees from Ghent University, and I'm here today with my co-organizers, Maya Rucker from Imperial College, Kamal Singh from Heriot-Watt University, Mohamed Noura from Oslo University, and Marcel Moura from Oslo University. And I will now give the word to Kamal and Marcel, who will be chairing today's session.
Thank you very much, Tom. So today's first presentation will be given by Alessio Scanziani. Alessio has recently defended his PhD thesis at Imperial College London. He worked on three-phase flow in porous media for enhanced oil recovery, CO2 storage, and other applications. He's currently working at International Energy Agency in Policy and Security Division. So he's also a passionate cello player, if I'm not wrong, right?
Yeah.
So before we start your talk, I would like to request our viewers to post your comments on the right-hand side of your screen. So the floor is yours, Alessio, and thank you for joining us today.
Hello, everyone. I just as Kamal said, I just graduated at Imperial College, and all of this work was developed during my PhD at Imperial College, which was founded by the Abu Dhabi National Oil Company, and I will also show some data coming from the International Energy Agency. My work was on three-phase flow in porous media, and I will focus on the dynamics and the effects of wettability. So as a general motivation of my work, we know that in the next year we are going to still need oil for our lives. This is still used in the industry and covers 80% of total primary energy supply. The International Energy Agency develops two scenarios. One is with the stated policy, which means that what's going to happen with the policies that are currently in the planet. And the second one is a sustainable development scenario, which is created by computing the CO2 cuts that we need to achieve our climate goals, like the Paris Agreement, and then they back calculate how much of the fuels we are going to consume for this scenario. And even in this sustainable development scenario, the role of oil will still be quite important. The consumption of oil will decrease, but not. We will not go to zero immediately. So we will still need oil, and also we know that easy oil is not really available anymore. So enhanced oil recovery will probably still play some of a role in the work. On the other hand, these graphs shows the emission cuts that we need to achieve to pass from the stated policy to the sustainable development scenario. And as you can see in these emission cuts, the role of carbon capture and storage is quite important. So when I started my PhD, I asked my supervisor, Martin Blunt, to work on three-phase flow in porous media, because when we try to combine the enhanced recovery and carbon capture and storage, we end with the simultaneous flow of three phases: oil, water, and gas inside the pore space. Pore scale studies have demonstrated to be quite helpful, because they can improve the predictivity of field scale simulations, which in the end are the ones that reservoir engineers use to optimize enhanced recovery and carbon capture and storage. And Imperial College has one of the most important facilities in the world for X-ray imaging, which allows this pore scale visualization. And in particular, when I arrived, people like Kamal, who is with us today, had already worked quite a lot on wettability at the pore scale and the role of dynamics using synchrotron X-ray imaging. So as I said, I decided to focus on three-phase flow, and in particular, what is the arrangement of these phases in the pore space, do oil layer form, and how the phases are trapped in the pore phase, which displacement patterns we see, and what is the influence of wettability. My first experiment was a water wet experiment using a cation carbonate. We performed this experiment in this cation carbonate without any pre-treatment of the sample, which showed water wet conditions. At these water wet conditions, we saw that when we have two-phase flow, as previously observed, oil goes in the big pores and the water stays the medium and small ones. However, if we inject gas, we saw that gas is the most non-wetting phase. It invades the biggest parts of the pore space and allows the formation of these oil layers sandwiched between the gas and the water, which is still confined in the smaller pores. We also compute the thickness of these layers, and they demonstrated to be thick enough to allow for a good oil flow, which allows to increase oil recovery. After this experiment, we moved to a synchrotron facility, and we performed a dynamic experiment. During this experiment was mainly the same as the one was performed at static, but at the synchrotron facility. So in this way, we were able to visualize the dynamics of the invasion of the fluids in the pore space. And what was the most interesting finding was the visualization of this double capillary trapping that happens when after the first oil injection, water flooding, and gas injection, we re-inject water. If we re-inject water after gas injection, we see that the water pushes oil, which traps the gas in the center of the pore space. These mechanisms allows the gas to be trapped in the pore space, and with a further water injection, the gas is not produced. This capillary trapping mechanism is very important for carbon capture purposes. Later, we performed another experiment where we pre-treated the cation sample using crude oil, and we modified the wettability of the sample. In this case, we noticed that the dynamics of the invasion changed a lot with respect to water wet, especially starting from the two-phase flow. So even before injecting the third phase, the gas, we saw that the invasion of water in the pore space was very different to water invasion in a water wet sample. In particular, we see that water advances as a connected phase through the center of the pores, in opposition to the going in the small pores as we saw in water wet. And also the order in which the water invades the pores are not in a decreasing order of pore size, as would be expected from a non-wetting phase invading a medium, but the order in which the pores are invaded it's not really fixed. So this means that the pore radius is not the only parameter controlling the invasion, but there should be another parameter. And we identified this other parameter to be the contact angle. We saw that the thermodynamic contact angle increased during the displacement because of the formation of pinned interfaces, which had to be overcame to allow for the flow. So this caused the thermodynamic contact angle to increase during the displacement, demonstrating that this has an impact in the flow dynamics. Later, we also injected gas in the same pore space, and again we saw that the gas invasion in mixed wet media demonstrated to be different to what observed in pore space in water wet cases. In particular, gas is still invading the biggest part of the pores, but it is in this case mainly displacing oil, and it's not displacing a lot of water. This is quite promising, of course, for oil recovery purposes. And again, the order of invasion is not really determined by the pore size, but we see that during the gas invasion, a wide range of throats are being invaded. Again, with subsequent water injection, we saw that the gas was still trapped in the pore space. In fact, when we inject water after the gas injection, the water displaces the oil, and the oil traps the gas in these small throats in the pore space. In this way, the gas in the end is trapped and it's not produced, which is promising for carbon capture purposes. So as a conclusion, we developed this methodology to visualize 3 phases inside the porous media with static and dynamic imaging. We analyzed pore occupancy, showing that in water wet, water occupies the smallest pores, oil the intermediate one, and gas the big ones, while in mixed wet media, the oil occupies more of the small pores, water is occupying intermediate pores, and gas is still occupying the biggest pores. We observed this double capillary trapping mechanism with which gas is trapped in the pore space. Gas injection improves oil recovery both in water wet media and in mixed wet media. We saw that the thermodynamic contact angle controls the displacement in mixed wet two-phase flow, and then wettability strongly affect the flow dynamics, influencing which phase is displacing which during the injections. As future work, we can look at the miscible condition. To use this, we can use this result to calibrate pore scale modeling. We can use the thermodynamic contact angle that we have used for two-phase flow and expand it to three-phase flow. And of course, the knowledge of this physics at the pore scale will certainly help the reservoir engineers to design the field scale injections. And there are also potential for non-geological applications. Thank you, and I think I will leave the word to the next speaker.
Thank you very much, Alessio. I will just take some minutes for questions. I have one, but I would like to invite anyone who has any questions to please write them down on the YouTube comment field. I have a quick one before. So you mentioned the thermodynamic contact angle. Could you explain a little bit how that is calculated? And I suppose you probably, do you do any kind of smoothing of the interfaces to calculate this the three-phase contact angle? And is there something that you have to be careful about the way you smoothen out these interfaces to calculate the angles?
Yeah, thank you for the question. I didn't have a lot of time to go through these details, but basically there are 2 contact angles computed in this study. One is the geometric contact angle, which is directly computed in the images using manual or automatic methods, but in the end we use the interfaces to measure the contact angle geometrically. And the automatic ones are done on segmented images, but not smoothed ones. For the geometric contact angle, we don't smooth the interfaces, but we have the segmentation in between. So this can influence the results. We have done some direct comparison with the manual measurements on grayscale images. So for the geometric contact angle point of view, we are quite confident that this is actually measuring what we see geometrically at the three-phase contact point. For the thermodynamic contact angle, instead, this is not directly computed from the images, but it is back calculated using other quantities like the curvature, interfacial areas, and saturations. So this was developed by, Martin Blunt published a paper recently on that, but basically it comes from an energy balance, which is balancing the change in surface area and the work that has to be applied to the system. In the end, solving the energy balance, you come up with a formula that I'm sorry I didn't put it there, but basically there is a contact angle as a function of curvature, saturations, interfacial areas, and interfacial areas between fluid and solid and fluid. Right. For the calculation of these quantities, we use smoothing. So for calculation of curvature, we use some smoothing mainly to try and overcome the voxelization of the interface.
Right.
And also we don't consider the part of the interface which is really close to the surface of the grain. So we consider the central part of the interfaces, and this was possible and easier for Kapton because we have these big pores that allow for the interfaces to cover quite a wide range of voxels. And the same goes for interfacial area between fluid and fluid, where we still have this smoothing as well as for curvature, while the interfacial area between fluid and solid hasn't been smooth.
Right, I see. Thank you. We have one additional question here, so let me just try to put it up on the screen like this. Okay, so it's from Reyhane Akbari, and the question is, any predictions on the consequences of phase transition on occupancy from supercritical CO2 to gas CO2 within the CO2 storage reservoirs, based on your observations?
Yeah, thank again for this very important question. Another thing I should have mentioned is that all my experiments are done with nitrogen and not with CO2. So this was the first time that we performed three-phase flow experiments, so we wanted to start safely and be sure that we didn't have other problems. However, now there is a student which is taking up my work, and he already has published something. It's actually Abdullah Lozani, and he has done some experiments using CO2, supercritical CO2, as asked in the question, and he observed, he's studying the consequence of near miscible conditions. He observed some similar results, but also sometimes something different. The main difference that he observed at near miscible conditions is that the gas sometimes is not anymore the most not wetting phase, but it can become the intermediate phase. But this is more linked to the near miscibility and not to the supercritical state. The supercritical state itself does not seem to really change much in the process.
Right. Marcel, do you have time? I can ask a quick question, or
yes.
We are late? Okay. So, Alessio, thank you for the presentation again. In the mixed wet system, you showed the thermodynamic contact angle is increasing with time, and I think the range is going more than 120, so it's clearly showing a non-wetting phase for brine phase. But you say it's a mixed wet state. What's the contact angle range you expect, or at least, or you analyze that you have in the system? Is it really a mixed wet system?
Yeah, that's another good question. I also, in addition to the thermodynamic contact angle, I computed the geometric contact angle, and the range of the geometric contact angle ranges from 45 to 175 degrees. So it's quite a wide range. So this is why I called it a mixed wet system. When the mean value is about 109 at the end of the first water flooding. So,
thank you.
Thank you.
Can I ask a very short, non-technical question?
Sure.
Alessio, you recently started working at the IEA. So I was just wondering if you have any perspectives from your new position on where the field should go to. This research.
Yeah. So by research field, you mean the port scale imaging, I think, or at least. So I think there are possibilities to for that in many industries. So as I said, the oil consumption is still going to be there, but we don't know how much of this will become from enhanced recovery. CCS is something that the IEA really promotes, but not everyone is agreeing with that. For example, I recently heard that the EU was not really in favor of it recently, but things can change in politics. However, I think that there are a lot of other applications that can be studied. For example, in fuel cells, for example, in reactors, I think would be quite important for the field to try and move into that, because we had, I think in Kamal experiences as well, we have tried to image other types of materials and flows of other fluids, and many very interesting things can be found there. So I would encourage the academia to also try to move there. I know that for the founding it's not always the easiest thing to do, but if they can squeeze here and there something on fuel cell, nitrogen, I mean, this probably will require a long discussion, but yeah, thank you for the question.
Right. Super. Thank you very much, Alessio. So if you don't have any more questions, I guess we can move on to our next speaker for today. And the next speaker is Bauyrzhan Primkulov. And Bauyrzhan is a PhD student at Professor Ruben Juanes' group at MIT. And he studies two-phase flow, multi-phase flow in porous media. And he mentioned that whenever he's doing his research, he spends most of his time either stuck or wrong. So I think this is a very honest description that many of us share. And yeah, we'll move on with his presentation. I just want to mention briefly here that just by chance I noticed that as Tom mentioned in the beginning, the Tea Time Talks is complementary to this geoscience webinar. And both Martin Blunt and Ruben Juanes, so the supervisors of the two speakers from today, have presentations on the geoscience webinar. So perhaps it's something there. It's also somewhat related to what they are presenting here today. So you're welcome to see that too. So okay, we can move on with Bauyrzhan.
Hi everyone. So before I start, I wanted to thank you for the introduction and thank you guys for generating the space for the rest of us to present our work. And today I'll be talking about our recent efforts on extending Lenormand's phase diagram to account for wettability. So I'll start with a bit of a historical perspective. So Lenormand and co-workers back in 1980s, they started working on this problem of pattern formation during fluid displacement in porous materials. So the system that they had in mind is a linear displacement cell where they would saturate the porous media with the wetting fluid and start injecting a non-wetting fluid at different flow rates. Now they reduced the problem to two dimensionless numbers. So one is a capillary number, which is a ratio of viscous to capillary forces. And the second one is the ratio of the viscosities of the two fluids. Now, so if you think of the problem that way, you can generate, well, they generated a phase diagram that has been very influential since then. So depending on the two dimensionless numbers, you could map all of your experiments, or no, most of the experiments, into different regions. So a region in the right top corner, so that's a stable displacement, then invasion percolation at the bottom corner, and the left top corner is viscous fingering. So I will cover them a little more in details, but what I'll say for now is that so what they had in mind originally was drainage, so injection of a non-wetting fluid. So as a result, you couldn't map all of the experiments onto this phase diagram. And then around the same time, people started reporting that wettability. So the wettability is the affinity of the porous media to the two fluids. So wettability plays also a significant role in shaping the displacement patterns. So there was a study by Stokes and company. Lenormand himself makes a few observations. And then a bit more recently, there were studies where people systematically studied, the influence of the injection rates, here capillary number, and the wettability of porous media. So this study was done in glass bead pack. And then a favorite study of mine is the study of wettability and the injection rates in microfluidic chips. So from this point on in the presentation, I'll refer to these experiments as a benchmark study. So basically here, the pore geometry was a Hilly-Shaw cell where you would print a post pattern, cylindrical post pattern, confined in between the two plates, saturated with oil, and start injecting water at different rates. Now, the x-axis is the wettability. So you go from injecting non-wetting fluid to injecting a strongly wetting fluid. And the y-axis is the capillary number. You could think of it as injection rates. So that was a great starting point for me. And the first thing that we did, we tried to reproduce the experiments in the limit of low capillary numbers. So that's when capillary forces dominate. So there were some really nice studies by Chiplak and Robbins, again, late 80s, 90s, where they reduced the problem for the similar geometry to pore invasion events. So they defined burst, touch, overlap events. And what we did slightly differently here, we realized that for all three events, you could analytically find the critical pressures at which these events would take place. So by doing that, you can turn the model of Chiplak and Robbins into invasion percolation model, where you invade the pores with the lowest capillary entry pressures, and then you would invade them in a manner that's appropriate for these three events. So we implemented those three events. We added a corner flow to account for the third dimension. And we were able to reproduce reasonably well the experimental patterns from the benchmark study. So here you have roughly an x-axis. So you go from strong drainage to strong imbibition. So in strong drainage, you have patterns that trap fluid, the defending fluid behind the invading front. And as you move closer to weak imbibition, you get these more compact patterns that are not leaving much defending fluid behind. And as you move towards strong imbibition, you start getting a little bit of corner flow that just takes over at a certain contact angle. So the way these invasion patterns are generated is completely governed by the relative frequency of these pore invasion events. And that's denoted by colors here. So in drainage, you have mostly burst events. So burst events, also known as Haynes jump events. So in weak imbibition, so mildly wetting regime, you have cooperative pore filling events that dominate. And in strong imbibition, the corner flow events dominate. So they're most frequent. And after doing that, and since we could analytically find these critical pressures, it was relatively straightforward to extend the model to include the viscous effects. So people have known for a while that flow in porous media is very similar to currents in electrical circuits. So it was a study by Fat back in the 60s. So what they realized is, the Poiseuille law in flow in porous media is equivalent to Ohm's law in electrical circuits. So then conservation of mass is equivalent to Kirchhoff's law at each node. And the only step that was left to make it a two-phase description, two-phase flow description, was to realize that local fluid-fluid interfaces can really be represented by a combination of batteries and capacitors for this geometry. So a capacitor, typically it's used to store charge. So you would build up charge up to a maximum, after which you get the dielectric breakdown, you break it. Similar way with the interfaces, you build the interface curvature up to a maximum, and then the invading fluid invades the pore. And then you move the interface, that is, you move the capacitor to a new location. So that way you reduce the fluid-fluid displacement problem to a series of linear equations that you advance in time. And if you do that, you can generate the whole range of flow patterns that were observed experimentally in the benchmark study. So key ones to note is so viscous fingering at the top, and then viscous fingering with a bit thicker fingers, in wetting conditions. So then invasion percolation in this corner, and then cooperative filling. And in a quasi-static limit, which is not a part of a dynamic model, you go into the corner flow. Now that we've went this far, it was just really one more step to try to run a whole bunch of simulations and really try to extend Lenormand's phase diagram to include wettability as a third axis. Yeah, but before I go there, I'm going to briefly describe the characteristics of the principal flow regimes. And I'll start with stable displacement. So stable displacement happens when you inject more viscous fluid into porous media saturated with the less viscous fluid. So during the injection, what you get is the pressure at the injection port grows monotonically, so it increases. Then the patterns that you generate, they're very symmetric. So in this case, it's a perfect circle that grows gradually. And then there are two key parameters that we watch out for. So one is the fractal dimension. So fractal dimension, it describes the complexity of the shape. So here, fractal dimension is close to 2, which means it's a very compact shape. So the second parameter that we define is the activity index. So it's just a measure of what fraction of the pores have appreciable flow. So keep those in mind. Now we move to viscous fingering. So in viscous fingering, as you inject, so the injection pressure monotonically goes down with time, and you develop these fingers that focus the flow within the main branches. But the pattern still is quite reasonably symmetric. And then most pressure drop takes place in the defending fluid, because viscous fingering happens when invading fluid is less viscous than the defending fluid. So in here, the much less of the front is active, which means mostly the fingertips, they have some pore activity. Most of the interface is still. Yeah, and the fractal dimension is between 1.6, 1.7, which is what other people also report in the literature. Now we go to invasion percolation. So that's a capillary-dominated regime. And you could see that here you invade the pores in invasion clusters. So you invade one part of the porous media, then you move completely to a different spot. So as a result, the patterns that you get, they're not radially symmetric at all. So here, the invading fluid has no clue where the outer boundary is, and as a result, it just explores invades the pore spaces in the order of lowest capillary entry pressures. As a result, you get a pressure signal that's very intermittent, and as a result, the flow is also very intermittent, changes direction frequently. So here, the fractal dimension that you calculate is similar to what is reported in the literature, and the activity index that we defined is very low. So which means you have only one pore at a time that's really active. So if you move this regime to a wetting condition, then you get very similar flow, but it is compact. So again, you invade the pore space in invasion clusters. The flow is very asymmetric. You get the intermittent pressure signal, and only a fraction of the pore space is active. Now that I've defined these 4 principal flow regimes that are captured in the dynamic model, you can do something to try to build the diagram. So what we do, we run a whole bunch of simulations to fill this space. So you have 3 axes. So one is viscosity ratio, capillary number, that's what Lenormand originally had, And then we add the wettability, so measured through the contact angle. So then you can use the activity index to separate viscous dominated flow from capillary dominated flow. And then you get the surface that separates it. So we choose a value of 2% activity that nicely separates the two. Then what you could do, you could separate compact shapes from non-compact shapes, and that's easily done with the fractal dimension. So if the fractal dimension is close to 2, that means you have a plane or like compact shape. If it's close to 1, that means you have like something like a line. So in this case, you easily separate the two, and really what we're trying to do, this. So we're trying to separate these 4 principal flow regimes based on, this characteristic: compact versus not compact, capillary dominated versus viscously dominated. So then we choose these threshold values, and you get the picture of Lenormand's phase diagram now extended for arbitrary wettabilities. So the front phase is what Lenormand had originally. So you span regions of viscous fingering, invasion percolation, and stable displacement, and then you get typical invasion patterns. But as you change the wettability from drainage to weak imbibition, you move into a region that has significant amount of cooperative filling patterns. Now, our dynamic simulations are limited to this box, but if we combine it with our quasi-static model published earlier, you could also infer how these shapes change outside the dynamic model. So in the limit of capillary numbers of 0, so quasi-static limit, you get the same transition from invasion percolation to cooperative filling, but then at the contact angle of around 40 degrees, it sharply transitions to corner flow. So corner flow, not part of the dynamic model, but we can still say something about the full shape of the Lenormand's diagram with a combination of 2. Now, of course, so something is left, this region is empty, and we leave it for future work. Another side effect of this project is, you could look at order and disorder. So the pore scale disorder, how it influences the patterns that you generate. So in viscous fingering, if you have like a regular lattice of posts and you introduce a little bit of randomness, well, different degrees of randomness, you generate patterns that have, so in our case, 6-fold symmetry, and then they break into something a bit less symmetric. So something that reminisces something similar to diffusion limited aggregation patterns for more disordered porous media. But overall, this more disordered porous media patterns, they're very similar to what we've shown in the Lenormand's diagram. And of course, what we simulate here has been observed experimentally by Chen, Wilkinson, and others more recently. So you can do the same thing for capillary dominated regime, and in capillary dominated regime you can see also an interesting interplay of these different flow regimes with the pore disorder. So invasion percolation patterns, they're really not so sensitive to disorder, and you get very robust, very similar patterns regardless of the degree of disorder, which is very interesting. Now, if you go into cooperative pore filling, then you get patterns that mimic the lattice structure that you impose to something a bit more disordered as you increase the degree of disorder. And again, so similar things have been observed experimentally, which is really nice to see. Yeah, so I'm gonna end the talk here with some basic takeaways. And really, because this is an ongoing work, more insightful conclusions are coming. Yeah, thank you.
Oh. Thank you very much, Bauyrzhan, for this fantastic talk. So it's a great messages at the end. I've got a quick question. How easy or how difficult in modeling part to add another dimensions in it, like third dimension it, in terms of modeling only?
Yeah, so it was fairly easy in the limits that we captured here. There is a difficult part. So the difficult part is corner flow at higher capillary numbers. So in that part, what people have observed is you have these wetting films that go ahead of the invading front, and those are really not so natural to capture in core network models. So yeah, so either we have to, and it's actually something we're thinking about. So either we have to go to like not too high of a capillary number so that we avoid that regime, and then you could capture it, or or you go to something else to continue models. Now, another interpretation of your question is the beat packs. So extending it to real 3D models. So that's also, I think, the Chip Black and Robbins' model, you could extend it. And there's actually a summer student working on it. Hopefully he gets through it. Yeah, but the dynamics is far ahead.
Sure. Cool. Thank you for that. If in the studio anybody has questions, in the meantime, if somebody is posting the question, please feel free to ask. If just a quick question, I think in terms of the contact angle you mentioned, they are like advancing receding contact angles or equilibrium contact angle.
Yeah. So here we assumed perfectly smooth solid surfaces, which of course they're never smooth in real experiments. But yeah, so for now we completely neglected so we neglected hysteresis, we neglected dynamic contact angle effects. Yes, like idealized.
Sure, fair enough. Yeah, thank you. We got one question from Enrico Segre. So he says, nice talks. Could you repeat your definition of the activity, lambda?
Yeah. So, okay. So, Serge, nice to meet you. Oh, sorry, Enrico, nice to meet you. Really nice paper that really motivated some of the early work here. So the way we define the activity index is a fraction of pores that have appreciable flow rate. So we take all of the pores, we kind of threshold the flow rates. So that is a bit arbitrary, of course. And then you take the fraction of pores that meet that threshold.
Okay, thank you. If anybody has another question from the studio before we wrap up the session. There's one, give me 1 second. There's another question coming up. Yes, it's second question by Segre. Why did you choose lambda as an indicator rather than any other, like interface length, number of trapped inclusions? Yeah.
So the way we were doing these simulations, so in order to make it a bit closer to the real experiments, apart from the pore, geometric disorder, I was also introduced a small disorder in wettability so that I could run the same simulation several times and get different realizations of it. Yeah, so that way, every time I would run a simulation, I wouldn't get exactly the same results. And as a result, so this activity index, we tried a few other things, and activity index seemed to be a one that produced smooth interfaces, which what we were going for. Yeah, so there are other measures. So let's say like symmetry. symmetry could be, radial symmetry could be a really good measure of separating these different flow regimes, but that didn't generate a boundary that was very smooth. Yeah, so there is a bit of randomness from. I would have to run like orders of magnitude of more simulations to get a smooth interface.
Okay. Thank you for the explanation. I think we can now wrap up the session. Thank you very much once again, Bauyrzhan, for joining us today and giving us this great talk. And we wish you good luck for your future career, and would like to see more presentation in the future. Yeah. Okay, so our next talk in 2 weeks will be given by Alex Demo, who will talk about 3D printing and flow in porous media. And the second speaker is Manuela Oliveras from Hesse University. She'll talk about dissolution and precipitation processes. Sorry, I forgot to tell Alex is from Heritage University. So join us in 2 weeks, and we look forward to seeing you there. And I would like to thank you again to our audience to send us all the beautiful comments and criticizing in wherever we are making mistakes. Please do send us more comments and help us to improve our experience with YouTube and also with the presentations. You can contact us on porousmediatt@gmail.com. With this, we'll say bye, and we'll thank you to all our speakers and all the audience who joined us today, and everyone in the studio, the online studio. See you in 2 weeks. Ciao.